Hello, my name is Klas and I work as a research scientist at the German Aerospace Center, or short DLR, in Braunschweig, Germany. And I would like to present you today results from the research project F-RELACS, which was a cooperation of the DLR and the companies TWT Science and Innovation from Stuttgart, as well as Sound Reply from Cologne. Specifically, I would like to introduce you to our developments of a data privacy concept for a frustration-aware in-vehicle system. First, I will motivate why frustration-aware systems are needed and why data privacy is an important issue here. Then I'll delineate the concept and its evaluation in a user study. And finally, I would like to share our key insights from this research with you. So why do we need frustration-aware systems? Frustration is an affective state that is triggered when goal-directed behavior is blocked. Actually, this often happens in the vehicle due to situations such as red lights or traffic jams, as well as annoying interactions with the in-vehicle infotainment systems. Frustration may lead to aggression, reduced driving performance, and diminished comfort. So that the idea is to develop a frustration-aware system that is capable of detecting and mitigating the driver's frustration. The envisioned frustration-aware system is based on recognition of the user's current frustration level, utilizing real-time driver monitoring. It is envisioned to extract information about the user in real time from physiological data such as electrocardiogram or electrodermal activity, as well as video streams of the participant's face and body. This is combined with context monitoring in order to additionally acquire information about the causes for frustration. The different streams of information are fused and interpreted using machine learning methods. In case frustration is detected, the system supports the user in the regulation of the frustration by means of a voice user interface. However, this kind of smartness comes at a price. For being able to detect the user's frustration and adapt to it, a lot of data from the users have to be recorded, including video streams and physiological data. These data may allow identifying specific users, so that data privacy and data sovereignty issues need to be considered when developing frustration-aware systems. In addition, it has been shown that a consideration of data privacy in the development process increases the acceptance of smart systems. Therefore, the goal of this research was to develop a data privacy concept for our frustration-aware system and evaluate it in a user study. Let me quickly introduce how we came up with the concept. For developing the data privacy concept, we first identified relevant resources, namely the General Data Protection Regulation from the European Union and the guidelines, a set of proposals for improving data protection in science that were developed in the GUIDE project. Our data privacy concept integrated the most relevant proposals from these sources and generally is based on the principles privacy by design and privacy by default. In total, the concept includes 9 data privacy criteria, namely earmarking, optionality, transparency, data minimization or data necessity, data storage despite real-time capability, optional individualization, data access, data privacy control, and adherence to standards. Based on these criteria, we formulated 23 concrete measures that describe how to realize data privacy specifically for our frustration-aware system. In order to evaluate the concept, we presented these 23 concrete measures to 96 participants in an online study. Participants could evaluate the measures on a 6-point Likert scale from 1, which means not acceptable, to 6, which means optimal, and provide free comments. In general, the evaluation was quite positive and the average rating for all measures was 4.7 on the mentioned scale from 1 to 6. The measures for the criterion optionality received the highest average evaluation with 5.2 and the measures for data access and data storage despite real-time capability received the lowest ratings with 4.4. It has to be mentioned, though, that this is still corresponding to rather sufficient. In the following, I would like to show you two specific measures and their evaluation. One measure from data stored despite real-time capability with a very low rating, and one measure regarding optionality with a very high rating. The measure that received the lowest evaluation was for real-time processing on offering a natural voice interaction to improve the user experience. The voice data is analyzed and stored by third-party services, such as from Google or Amazon. No personal data such as name, age, address, etc. is forwarded to these services. As you see in the plot below, pretty many users provided a very low rating with a 1 corresponding to not acceptable, and only very few found this measure optimal and provided a rating of 6. Thus, we can conclude that forwarding voice data should be avoided whenever possible. Here it has to be mentioned that this forwarding was necessary because the development of the language understanding software was not part of our project, so that we relied on commercial software at first for this task. But these clear results should be kept in mind when developing emotion-aware systems. On the contrary, the measure with the highest rating was the following. The user can deactivate the system at any time by pressing a button and thus stop the data recording. In the plot below, you see that roughly 60% of the users said that this is optimal, and only very few provided rather low ratings of 1, 2, or 3. Hence, optionality is very important so that the user can stop the processing if she or he does not want to be recorded anymore. Taking all of these results together, we can say that the measures were in general adequate, but some improvements for a commercial frustration-aware system are needed. The user-oriented process we took provided us with some interesting insights for making data privacy a reality for frustration-aware systems or driver monitoring systems in general that I would like to share with you in the following. So, our take-home message from this research are the following 3 key insights. First of all, we learned from the evaluation that users wished an independent evaluation of the data privacy concept. This means that independent bodies and not the manufacturer should evaluate whether an emotion-aware or general driver monitoring system complies with data privacy guidelines. In addition, we would recommend to avoid cloud processing whenever possible. Many participants propose to use offline services for speech processing. Hence, people would likely also dislike if systems could use cloud software for processing physiological or video data of the users. Thus, designers of emotion-aware systems should try to avoid such cloud services and integrate software with local data processing instead. In our research project, we made use of cloud software to focus the resources, but for a product, this should be avoided if possible. And last but not least, we believe that data privacy is an aspect of UX and usability. Information displays that notify users about the processing of their data should be designed with great care, so users easily understand what happens. To achieve transparency about this, the human-centered design process needs to include this goal from the beginning instead of adding information displays about the data used to the finished product in the end. So please start thinking about data privacy when you begin developing your frustration-aware system and not only in the end. Data privacy is an aspect that should be considered right from the beginning. Having said these words, I would like to thank you for your attention and would be happy to discuss the results with you. Find my contact details on the slide or in the paper. Thank you very much. Finally, I would like to give credits to all people involved in the project F-RELACS and say thanks for the funding to the German Ministry for Education and Research.